let's start that. Let's get going with today's material. So yeah, today, hardly any new material, just a bunch of examples of what we covered in Chapter 4. I'm pretty sure I said some things wrong in Chapter 4, a couple things wrong in lecture. So hopefully we don't make any mistakes today and everything makes sense. Okay. Often examples help clear concepts. So let's just jump right in. Bunch of examples, bunch of problems to solve. First problem we're going to solve. So in the first problem, we got some gymnasts hanging from a rope. So here's the ceiling, here's the rope, and some gymnast is hanging onto the rope.
What does gymnast mean?
Someone who does gymnastics.
Oh, gymnast.
Like an acrobat. And they have a mass of 50 kilograms. 50.0 kilograms. So we have three significant figures for this problem. Okay. So our job is to A, calculate their tension, and B, calculate A, their weight, and then B, the tension in the rope that they're hanging from. Okay, what's the weight of the acrobat?
It's mass times gravity.
It's just mg. So it's 50g, whatever that is, newtons. Right?
What about gravity?
So a little less than 500.
Oh, I guess it's not.
G, that's a G. 9.8. 50 times 9.8.
I see.
So a little under 500 newtons, right? 490 newtons. So there's our weight. Okay, B, what's the tension in the rope? At both ends. Now notice that there's tension in the rope pulling on the gymnast up, and then there's tension on the ceiling from the rope pulling down. Right? Does that make pretty intuitive sense? The gymnast is hanging in the air. Her weight is pulling her down. If we did a free body diagram for the gymnast, her weight's pulling her down. So she's not moving, so there must be some force pulling up. That's the tension of the rope. So the tension at the bottom of the rope has the same magnitude. It points in the opposite direction, but has the same magnitude as her weight. Does that make sense?
No, that doesn't make sense. When watching your lecture last week, it didn't make sense for when you're pulling on something and it's going this way as well.
Imagine I give you one end of a rope and I have the other end of the rope.
Okay.
You and I start pulling on that rope, but neither of us are moving.
Yeah.
Which way is the rope pulling me? Towards you. Which way is the rope pulling you? Towards me.
Okay.
That's the tension in the rope. Now I'm not moving, which means that the friction between me and the floor. If I was standing on a frictionless surface holding a rope and you pulled it, I'd move forward.
Yeah.
Since there's friction between me and the floor, there's a friction force holding me back. So I'm being pulled forward by you, that's the tension in the rope. Friction's holding me back, so I'm not moving. Those forces must perfectly cancel out each other.
Okay.
Same thing's happening on your end. That's you and me holding a rope. Here the gymnast is hanging on the rope. Her weight's pulling her down. She's not falling. She's not moving. So there must also be a force pushing her, pulling her up. In this case, it's the tension of the rope pulling her up.
And how does the rope pull her up though? When it's falling because of gravity.
It's attached to the ceiling.
Okay. So if it's attached to the ceiling, how does it still pull her up? I don't get that. Is it the same concept as our roping?
Yes. Okay, imagine I'm holding the rope now and I'm just holding it really tight.
Okay.
And you pull the rope really hard.
Then I'm going to fling back.
No, you pull the rope that way as hard as you can. So you're pull the rope that way.
Okay.
But you're not moving. That means the rope's also being pulled this way.
I see it.
Okay. So the tension in the rope since the rope's attached to the ceiling, there's tension in the rope pulling her up, and her weight's pulling her down. Those perfectly cancel out.
Okay.
Otherwise, she'd be moving.
Yeah.
She's not.
Okay.
So the forces must perfectly cancel out. Therefore, the magnitude of this force must equal the magnitude of this force. They point in opposite directions, but they have the same magnitude, same length.
Okay, what if she was accelerating downward? very slow speed.
That changes the problem. If she were accelerating downwards, then her weight is dominating the tension, and so her weight outdoes
So
the
her
tension.
weight would outdo the tension. Not the
Would have to
tension
be
outdo
bigger.
the weight.
If she's moving down, if she's going the way that this arrow is pointing,
Okay.
then this arrow is bigger.
When is it the case that the tension is more than your weight and it pulls you up?
When that could be a system like this. Here's a pulley. I'm right here, and I'm pulling the rope down, and you're hanging on it, and I'm pulling you up.
Oh. Okay.
All right. So the tension in the bottom of the rope is just the same as her weight, just pointing in the opposite direction. And the tension at the top of the rope is exactly the same as the tension at the bottom of the rope. So that, once again, is still just 490 newtons. Good?
Why does it have to be the same all the way through it?
Because the rope's not moving too.
Yeah, because the rope isn't moving. And so if you do a free body diagram for the rope, it has what are the forces acting on the rope. You have her weight pulling the rope down, and you have the ceiling pulling the rope up, the force from the ceiling.
Okay.
Those have to be equal to each other, right?
Mm-hmm.
And for every action, there's an equal and opposite reaction. So the tension in the rope is canceling out that. The tension in the rope here is canceling out that.
Oh, I see.
So they're all equal, assuming the rope is weightless, which we were assuming in this problem. Good? Okay. So that's the first problem. Second problem is we do the exact same problem, but now we assume the rope has some weight. So I'll reset up the problem here. Let's draw the rope a little bit fast so we realize it has some weight. We got a thick rope here, and now we've got some person hanging onto the rope.
Okay.
The person still has a mass of 50 kilograms. The weight of the rope here is 120 newtons.
Okay.
Good? So now, in this scenario, so we're not doing that, new scenario, we're supposed to find the tensions in the rope. So if we did a free body diagram for the rope, we kind of need to draw two forces here. We have one force pulling down on it
From the ceiling or from the person?
from the person.
Okay.
So we have the weight of the person pulling it down, but we also have the weight of the rope pulling it down,
Okay.
right? And then we have the force from the ceiling pulling it up.
And we're assuming that she's holding still, right?
Yeah, the whole system's static.
So then you just add the two weights together and that just equals the same as the tension, yeah?
So let's start with the tension at the bottom. What's the tension at the bottom of the rope going to be?
490.
Maybe start with the, it's what?
490 plus 120.
Tension at the bottom of the rope?
Yes.
Maybe we should have started with let's just draw this out. Here's the rope, right? And then here's how's the best way to make this intuitive? The only thing creating tension in the rope is weight, right?
Yeah.
Yes.
How much weight is there at this end of the rope?
Just 120.
No, just her weight.
90.
490 newtons.
Well, where does the weight of the rope? Where is that?
It's up here is where you feel the weight of the rope.
How is the weight at the top? Isn't the weight supposed to be at the
Imagine
bottom?
for a second that there's a chain of 3 people, and you're a part of this chain.
Okay.
So you have a bunch of people hanging in the air, holding each other's hands. So this person's hanging on to some bar on the ceiling, right? And then they're holding some other person hanging in the air. And they're holding some other person hanging in the air.
Okay.
You with me?
Mm-hmm.
Who has the hardest job?
The guy on the top.
The guy at the top. He has to hold more weight.
Yeah.
He has to hold his weight and her weight and her weight.
But isn't
I
it
see.
top tension
I see that.
pulling it down?
So the tension at the top is canceling out the ceiling force. So how much force do you have to apply to hold up the rope? you have to hold up the weight of the rope and the gymnast. Whereas right here, you just have to hold up the gymnast.
Oh, okay.
So the tension at the bottom of the rope is still only 490 newtons. Nothing changed in the scenario at the bottom of the rope. The bottom of the rope has no clue how much weight is above it.
Okay.
Right? If you were right here in this chain, say you're at the end of the chain and you're blindfolded. If you're the last person, you're blindfolded. You have no clue how many people are in that chain. There's no way for you to know.
Yeah.
That's like the force the atoms at the bottom of this rope are feeling. They're only being pulled down. Right? So the tension at the bottom is still just 490 newtons. It's the tension at the top where you have to account for also holding up the weight of the rope. And so in this case, then what is it?
In that case, it's 120 plus 490.
Yeah, so it's 610 newtons.
Yeah.
So the tension at the top is bigger than the tension at the bottom. Because at the top you have to hold up the weight of the rope and the gymnast. At the bottom you only have to hold up the weight of the gymnast. Make sense? And so nothing's moving if you were to add up all those forces. If we did a free body diagram for the gymnast we have the weight of the gymnast, and then we have the tension at the bottom, and those have to be equal but opposite.
Yeah.
If we did the free body diagram for the rope we have the tension at the top pulling it up, right? And down here, we have the weight of the gymnast
Why are the tensions
plus the weight of the
going-
rope.
Why are the tensions going in the same direction? Isn't at one point in
Sorry. I'm saying the tension at the top is equal but opposite to the force that the ceiling applies on the rope. So the force from the ceiling. Okay.
And where's tension?
The tension at the top, that is the force opposite to the force that the ceiling applies on the rope.
So isn't that being added with the weight?
These two create that tension.
Oh, okay.
That makes sense.
I mean, I could have written out all three places on the rope. So at the top of the rope, what do we have? So we'll draw it like this. At the top of the rope, the forces, we have the force from the ceiling pulling up, and then we have the tension at the top. And then right here, we have the tension at the bottom, and we have
Wait.
the weight of the gymnast. But the problem is where do we put the weight of the rope? In this picture, if we draw it like that, like right here. So, which however you draw it, you like lose something.
Yeah.
But does it make sense?
Yeah, that does.
Mm-hmm.
All right, let's do another one. An engine of weight W hangs in a garage on these angles. So let's set that up. Well, we can just talk about this picture since we have it on here. So this is a chain. This is a chain. There's some circle pieces together here, then some chain, and then some heavy engine that they're holding up.
Okay.
Make sense?
Yeah.
And the engine is pulling down with the weight W. So we know the weight, it's W, that's a given number, whatever it is. And I think our job is just to find the tensions in each chain now.
Okay.
You with me? Okay. So first off, the whole system's static, which means in the x direction our forces are add up to just one direction at a time. Is this system moving in the x direction?
No.
No.
No. So my forces in the x direction add up to
0.
0.
Okay.
Okay, so what are all my forces in the x direction?
Just T2.
I have T2 plus what else?
Cosine of T3, right?
R2.
Since I'm just going to use quantities here, I'm just going to pick a convention. So I'm going to call T3, I'm going to set my coordinate system like this. You with me?
Yeah.
Okay, so T3 is going to be pulling in the positive direction if we think about what's pulling on this ring, and T2 is going to be in the negative direction, and together those add up to 0. So in other words, I'm going to write this as
T2 minus.
T3 minus, T3 is going to be the positive one.
Oh, T3x minus T2.
So I'm going to be doing T3 this way, T2 this way, and then T1 this way.
Okay.
And all three of those forces add together are creating nothing on that circle piece. And then that will give me the magnitude of each of these tensions, which is what I'm looking for.
Oh, I see.
Good?
Yeah.
Okay, so T3 what? How do I get the x component?
Cosine.
Look at the picture, don't blindly answer.
Yes.
Is it cosine?
I think so.
Okay, it is.
Okay.
Just want to make sure because we go a lot of times back and forth between sine and cosine. Don't think just because cosine works on a circle for giving me the x, it's always just cosine for the x. In this case it is. Cosine is going to give
How do you
me...
know whether it's on the x or the y?
Look at the picture.
Okay.
Here's our triangle. Did I want this side or did I want this side?
You want this side.
I wanted this side, right?
How do you know that this side is cosine versus this side?
My angle's right there.
So to the
You
right
want me to
hand-
redraw that triangle? Let's redraw this triangle. Flipped upright for you.
Oh, okay.
That's that same exact triangle.
Okay, I see.
Okay, so that, in this case, happens to be the x. We'll solve lots of problems where that's not the case. So don't get confused by that. Anyway, so there's our triangle. So in this case, T3 cosine of 60 degrees plus T2 is completely in the x direction. This is equal to,
Wouldn't it be minus T2?
oh, thank you. Yeah, otherwise we have to treat these as vectors, which we don't want to do. Because the other way I could have written this is the total force in the x direction is equal to, well, that's not even the same. Doesn't matter. Okay. So, and this whole thing is equal to 0, right? Because it's not moving in that direction. So that tells me that T3 times, what's cosine 60 degrees?
Cosine of 60 degrees is root 3 over 2.
Try again.
1/2.
1/2. Took a 50-50 shot, and you missed. Is equal to T2, right?
Okay.
Just moving T2 to the other side.
Yeah.
So I got T3 is equal to 2T2. So I got that relationship so far.
Wait, so the force of T...
The
of
tension in this chain is
The tension.
double the tension in this chain.
Okay.
Which, look at the picture. Which chain has to do more work?
This one.
Obviously, this one's
Yeah.
doing more work. Yeah. Has a harder job. Shouldn't say it's doing more work. We'll define work tomorrow.
Okay.
Okay. So we know a relationship between T3 and T2. Now let's look in the y direction. I know that f of y in the y direction also adds up to 0 on this chain, right?
Yeah.
So we're going to call that way up and that way down, or that way positive, that way negative. So I know T3 sine of 60 degrees minus T1 is equal to 0.
It's the same thing.
Almost the same thing, slightly
Oh.
different. But before I solve this out, well, we can solve this out first and then come back to it. So root 3 over 2, T3 is equal to T1, right?
Yes.
I guess I'm going to want T3 in terms of T1. So T3 then is equal to 2 square root of 3 over 3 T1. Right?
How do you do that?
Multiply both sides by 2 over the square root of 3. This is 2 over the square root of 3. 3 is square root of 3 squared. hard. 2 over the square root of 3 times top and bottom by root 3.
But if you times it by root 3 over root 3, don't you have to do the same thing to the other side?
What's root 3 over root 3?
Oh,
Okay,
okay.
good? T3 equals that. So let's now put this up here. T3 is equal to 2 square root of 3 over 3 T1. And then, so finally, what's T2 in terms of T1? So T2 then, in terms of T1, is going to be half that. T2 is half the size of T3. So if T3 is equal to that, then T2 is equal to root 3 over 3 T1. With me?
Yeah.
Now, why am I writing them all in terms of T1? Well, because what do we know T1 is equal to in terms of its magnitude?
The weight.
The weight.
The weight. So, I know that T1 is equal to weight. I know that T2 is equal to root 3 over 3 of the weight. And I know that T3 is equal to 2 square root of 3 over 3 of the weight. So you give me the weight, whatever the weight is, I can now tell you all the tensions in all those chains.
That's pretty cool.
Make sense? Common thing as you get further into physics, you're going to be given a lot of problems where you don't actually work with numbers. You just work with variables like this. So, I don't know if that makes you uncomfortable or not. You'll eventually get to a point where it doesn't matter if you're given numbers or just variables, because you'll just solve it with variables and then at the very end plug in your numbers. But a lot of people are disheartened by that. Okay, next. Okay, so this one, we have a car on a ramp. Whatever. We have a car on a ramp, assuming it's frictionless, the tires can roll, the cars are neutral. The ramp is at some angle alpha,
Okay.
and the car is being held on to the ramp by some chain. Good?
Mm-hmm.
So that's our scenario. We know the weight of the car is W, so free body diagram for the car over here. Sometimes it helps to put the single in there as well. Free body diagram for the car. We know we have weight W pulling it down. Right?
Yeah.
Well, we also know we're going to have tension in the chain pulling it up that way. And we also know we're going to have a normal force pushing it that way. And those are going to be the three forces acting on the sink.
Okay.
Let's see what we're after. W is held at a slanted ramp by a chain as shown. Find the tension in the chain and the normal force on the car. Okay, so we're looking for the normal force and we're looking for the tension. The car, we're assuming, is not moving. And we're assuming that it's in neutral, so no friction.
Yeah.
So no frictional forces. So these are the only forces. So all these forces add up to
0.
0.
It's not moving.
Now, completely arbitrary how you choose your coordinate system. Doesn't matter how you choose your coordinate system. I'm going to choose my coordinate system like this. Here's X, here's Y.
Why?
Because then my normal force is completely in the Y direction, my tension is completely in the X direction. I just have to break up my weight into X and Y components now.
I see.
There's no reason that's better. Probably is going to save us some algebra to guess. But you could have put your coordinate system like that, solved the problem, should have gotten the exact same thing. Shouldn't change anything. Okay. So, I know tension is completely in the X direction. Normal force is completely in the Y direction. I need to break this weight vector up into its X and Y components now. Right?
Mm-hmm.
And so, draw our triangle. It's going to be something like that. And whatever this angle alpha is here, that's going to be the same angle right here, alpha. Right?
Okay.
And so this side, the y component of weight is what?
Your tangent.
What? This is the right angle. You always make your vector the hypotenuse of a right triangle.
Oh, so it's going to be your cosine.
Cosine. Perfect. So in this case, notice how it was cosine for the y direction. And then this one down here is going to be w times sine of alpha, right?
Yeah.
Perfect. Okay, so now we know that the sum of our vectors in the x direction is 0, and the sum of our vectors in the y direction is 0. And so we do basically what we did in the previous problem.
Gotcha.
Right?
Yep.
So I know that tension then is equal to what?
It's just equal to w times sine of alpha.
W sine of alpha. And I know that the normal force is equal to what?
W cosine.
W cosine of alpha. That was hard. We're done.
So if you know the angle and you know the weight, you know exactly what it's
Then
going
you know the tension and the normal force.
Okay.
Make sense?
Yeah.
Okay, finish those examples. Come over to these ones. Should have probably checked some of these as we were going. W sine of alpha, W cosine of alpha. Did the last one right. Okay, yeah, let me move over to the whiteboard. Get away from this chalk. Slide that. I think we're good. Okay. Next. Okay. So for this next problem, we have a ramp at 15 degrees. You're working in a quarry, pulling out big blocks of stone. So you design this ramp, and we're going to assume it's a frictionless ramp, that you're going to slide your stones up, your big stones. You're going to have a pulley there. And as you're pulling out the stones, you also need to get dirt in the quarry to fill in where you took the stones out of. So you're also going to dump sand into. So you also need to get sand down into the quarry. So what you're going to do is you're going to attach stones to a bucket. You're going to dump sand into the bucket, which is going to pull your stone up.
Okay.
Make sense? Now your stone has a weight of W1. The question is, what weight, if you make so that your bucket weighs W2, so let's say your stone weighs W1, your bucket weighs W2, and W2 is the perfect weight to barely get the stone going and keep it moving with a constant speed.
And it doesn't matter what the speed is, right?
Doesn't matter what the speed is.
Okay.
Remember, speed is relative.
Yeah.
If you're moving with a constant velocity of one inertial reference frame, that's not moving in another inertial reference frame. So there's always some inertial reference frame where constant speed velocity is 0. If you're measuring it as a constant speed in your inertial reference frame.
Okay.
So that's why when there's constant speed velocity, that's the same thing as holding still. The thought experiment to always remind yourself of that is always think about you and someone else in outer space, nothing else around. You're drifting this way a little bit, and so it looks like they're drifting that way a little bit. Who's really moving? Okay, so yeah, we got this thing moving with a constant speed, i.e. the net force acting on it is 0, no acceleration.
Okay.
Forces create accelerations. F equals ma. Okay, so let's draw the free body diagram for the scene really quick for just this stone W1. So I like to put a dotted line in for the ramp. Let me, well, I guess it doesn't matter as much. Obviously I drew the angle a lot bigger than 15 degrees, right? But it's 15 degrees, picture's lie. Okay, so pulling down on this sink, we have a force of W1, right?
Yep.
What's the tension in the rope pulling it this way?
Just the tension. How do you find that?
It's just the weight of this bucket.
Okay.
The weight of this bucket, we're assuming that the rope is weightless now. Always assume ropes are weightless unless stated otherwise. So the only thing pulling this up is the weight of this thing.
Yeah.
Right? You understand that that's a pulley, right?
Yes.
Pulleys don't apply force, they just change directions of forces. That's all a pulley does. Take something that was in the X direction and change it as its direction. Okay, so the tension then in the rope is just going to have magnitude what?
W2.
W2. And then finally we'll have normal force.
Yep.
Right? Let's see what we were after. How must W1 and W2 be related? Okay.
Those related.
Yeah. What do you know about the relationship between these two things? Well, once again, I'm going to call my XY on a slant like this. Here's X, here's Y. I know that the sum of the forces in the X direction are 0, right?
Mm-hmm.
And what are the forces in the X direction? Draw my triangle here. That's a right triangle. I know that this angle right here is 15 degrees, right?
So it's just sine of 15 degrees.
W1, we'll put that over here. So this side right here is W1 sine of 15 degrees, right?
Okay.
So I know that W2 minus W1 sine of 15 degrees is equal to 0.
Same thing.
So I know that W1 times sine of 15 degrees is equal to W2. That's the relationship between them.
Gotcha.
So you might ask a question, let's just plug in a hypothetical really quick. If I'm trying to pull up a block here that weighs 10,000 newtons, so the weight of that block is 10,000 newtons, how much weight of sand do I need to haul it up the ramp?
10,000 times sine of 15 degrees.
And is that going to be a much bigger number or a much smaller number or roughly the same?
Smaller. No, bigger.
Bigger number. So we take 10,000 and we multiply it by the sine of 15 degrees. And we get roughly 259. It's much smaller.
What?
It's much, much, much smaller.
Is that how pulleys work?
Well, that's just forces. That's how inclines work. Imagine you have to push something heavy. Is it easier for you to just lift it up? Or is it easier for you to have a nice, slightly steep ramp and you push it up the ramp?
Push it up the ramp.
Right. Pushing up the ramp decreases the amount of force that you have to use to lift it. You're going to end up doing the same amount of work. We'll calculate that tomorrow. Your work's the same, but it requires less force. You compensate less force with more distance. If you're willing to go more distance, you can use less force. If you want less distance, you have to use more force. So if I'm going to lift a box a foot in the air, I can either just take it and lift it, which is really hard, or I can take it down, push it on a really, really shallow ramp and slide it. Imagine that the ramp's frictionless.
Yeah.
Okay.
And once I get 1 foot in the air, I will have done the same amount of work. So you can compensate the force you need by making a greater distance. We'll do more with pulleys. But the amazing thing about pulleys isn't necessarily that. It's that with enough pulleys, I could take my fingers, go like this, and lift a ship. Lift a car, easy. With enough pulleys.
That's for
So,
real.
it's one of the, huh?
That's for real.
Yeah, and we'll calculate it.
Okay.
Basically, every pulley you use can divide the weight in half. Well, If I have 3 pulleys, I have to lift 1/3 the weight. If I have 4 pulleys, I have to lift 1/4 the weight, etc.
I see.
And we'll calculate that, and that will all make sense when we get to pulleys, but we're not there yet. Anyways, so there you go. So it's a lot easier, or it takes a lot less weight now to lift it up the ramp than the actual weight of the stone, which is why we use ramps, which makes perfect sense. Otherwise, we wouldn't use ramps.
Yeah.
Okay. Next one. The 200 kilogram ice boat accelerates from rest with wind blowing on it. After 4 seconds, it's moving 2 meters per second. What was the force? Or 6 meters per second? Okay. So an ice boat. It's like a boat, but it just has some blades at the bottom of it, so it slides on top of the ice. So we've got a boat-looking thing, and then it's got some blades at the bottom of it, so it can slide on ice. And then it's got its sail here, which captures wind. So when the wind blows, it causes the ice boat to accelerate forward.
Okay.
Okay? So I know that the mass of the ice boat is 200 kilograms. And the ice boat is going to be accelerated from rest by a constant force of wind, F. So draw a free body diagram for this ice boat. We've got its weight pulling it down. We've got the normal force pushing it up. And then we've got the force of wind pushing it forward. So obviously the boat's going to accelerate that way.
Oh, that's pretty straightforward.
Yeah. After 4 seconds, the boat is moving 6 meters per second. Find the force. So first we need to calculate the acceleration, then we'll use the acceleration to calculate the force.
Okay.
All right? So I know the initial velocity in this problem is what?
0.
V naught is equal to 0. And I'll set my coordinate system so it starts out at position 0.
Okay.
This is the one-dimensional problem. Everything's happening just in the x direction. We can ignore the y direction, right?
Why is that?
The force is completely in the x direction. So our velocity, our displacement, our acceleration, everything's just in the x direction. The boat's not suddenly jumping.
Oh.
Nothing happens in the y direction.
Okay.
Okay. So our initial velocity is 0. X naught, we're going to set it up so that it's 0. We know that our time is 4. 4 so we have 2 significant figures when we write our final answer. And we know that our final velocity is equal to 6. We're looking for our acceleration. What's the equation? We know it's a constant force, by the way. F is constant, so our acceleration is constant. So we can use our constant acceleration equations. So the equation we're going to use is v squared is equal to v naught squared plus 2a delta x. Yeah? That equation you've used on like all your homework problems, so you just now have it memorized.
Right.
I think I might make you guys derive that on the test.
Derive it? Okay.
Yeah, it's real simple calculus to derive it.
Maybe you should show us it again.
Acceleration is equal to acceleration.
Wow.
Oh.
Multiply both sides by v.
Okay.
So now we get this v, we write as dx dt. V, right?
Yeah.
Treat it as differential, so cancel out the dt's on both sides. So v dv is equal to a dx, where acceleration is a constant. Integrate both sides. Integrate from 0 to sometime t. Integrate from 0 to sometime t. What's the integral of v with respect to v?
Integral of just
V with respect to v?
v squared over 2.
V squared over 2, and we need to evaluate that from 0 to t. It's equal to, when you integrate that, you get a times x. Evaluate from 0 to t. V at time 0 is exactly what we mean by v naught, so that's v naught squared over 2 minus v squared over 2 is equal to a times x naught, or x minus x naught. Oops, I wrote this one backwards. You do your final minus your initial, like that, right? Multiply by 2, move the v naught to the other side, voila.
Okay.
good test problem.
But you don't know what your end position is. So can you use that?
Oh, do I
Yeah,
not?
you know your time.
After
Oh, I know my time. Thank
Aren't
you.
you just looking for
Thank you, thank you, thank you.
V
You're right.
equals V naught plus acceleration times time?
So V equals V naught. Yep, that's exactly what we want. Good catch. Yep, I read that as an X. So this is the equation that we need. Hopefully you know how to derive that one from acceleration to constant.
I think so.
You just integrate a constant.
Yeah.
Okay. When you integrate a constant, it turns into AT plus your constant. Okay. Anyways. So yeah, that's pretty easy. So V naught is 0. T is 4. V is 6. So what's our acceleration?
Why is V6?
That was given to us.
Acceleration is 3 over 2.
So 3/2 meters per second squared. Right?
Okay.
There's our acceleration. So now we can figure out our force. What's our force equal to then?
Divided by the mass.
We knew that the mass of this thing was 200 kilograms.
So it's just 200 times 3 over 2, so 1 point, so 300
300. 300 what?
kilograms.
300 what?
Newtons.
Newtons. Talking about force. Good?
Yes.
All right, next one. If the ice boat in that, if the ice boat in the problem we just talked about experienced a frictional force of 100 newtons, find F to keep the same acceleration.
What's friction in it?
Friction?
Yeah.
Friction is when you go and you push a box.
Okay.
If I'm sliding a box along the carpet and then I stop pushing, what happens?
It slowly comes to a stop.
It stops. What makes it stop? Friction. Friction is a force resisting movement.
Okay, so if it's resisting 100 newtons, then you just add 100 newtons to the F, right?
So free body diagram now for the boat. It's the same free body diagram,
Okay.
but now we have a force of friction pushing that way. Friction
Oh.
always opposes the direction of motion. Always.
So if the direction of motion is this way, then it's opposing it this way?
Sure, but then it needs to be on a ramp for there to be motion that way.
So like on the car one?
Yeah, like on the car one, or like just sliding a box. Doesn't matter which way you try to slide that box, it's always pushing back against you. Friction is. Right?
Is there such thing as a non-frictional force in the universe?
A
Like
non-
something that's frictionless, sorry.
Ideally, perfectly frictionless, no. But we can get really, really close approximations of things. I mean, I don't know, friction kind of implies you're sliding it along something. Throw something in the vacuum of space, there's no friction there.
Oh, I see.
I mean, technically there's a little bit of there's going to be a little bit of resistance because there's no such thing as a perfect vacuum of space. There's no perfect anywhere in physics. They're just really close.
So we just say pretend there is even though there isn't?
Yeah, we say it's a good enough approximation for the problem that we're talking about. It's like, I assume that as this falls through the air, the acceleration of the Earth was the same right here as it was right here. It wasn't. Slightly different. So absurdly small in the difference that there's no point taking that into consideration.
Okay.
But there was a difference. Or I assume that you and I experience time at the same rate. We don't. There's a slight, absurdly small difference, but it's there.
Isn't that difference really bigger though with time compared to a child versus an old guy?
No, it's absurdly small for two people who live their whole lives on planet Earth.
So what makes it feel massively different?
Experiencing time? Oh, you're just talking about a psychological perception.
Wow.
A psychological perception. Why does an hour seem long when you're a kid and longer when you're an adult? Because of what you have to compare it with.
So you make the comparison in your head and it makes you feel like time is going slower or faster?
What do you mean by feel? You still measure it the same. When I say you and I don't measure time exactly the same, I'm saying if you and I got together and we had perfect clocks and we perfectly synchronized them, so we both start our timers at the exact same time.
Yeah.
And we go and we live our lives and they're perfect clocks with as many points of accuracy in decimal places as we want. And we came back in 10 years and we compared our stopwatches, they'd have slightly different times. That's what I mean by we don't experience time at the same rate.
How does that happen?
Special relativity. You gotta learn basic physics before you can do the fun stuff. Anyways, so friction. So now we have friction, we have big F, and we now know for this problem, the boat is still accelerating that way at 3.5 meters per second squared. So ignore all the other information we were given. All we know this time is now the boat is accelerating that way 3.5 meters per second squared.
Okay.
3 halves, not 3. So our job now is to find the new force of wind. How hard is wind pushing on this boat if it's still accelerating that way at 3.5 meters per second squared if we introduce this force of friction, where our force of friction was 100 newtons?
Yep.
100 newtons. So now what do I know? I know that the force in the x direction is equal to, we'll now recall that F of wind since we're dealing with a couple forces, is now equal to F of wind minus our frictional force, right?
Yeah.
And I know that this is equal to our mass times our acceleration, ma.
Yeah.
So just 200 times 3 over 2, so 300.
It's just 400.
It's just 400.
Yeah, it's just 400.
300 plus 100, 400. So the force of the wind now, in this case, is 400 newtons.
Oh, that's not difficult.
No, all of these are surprisingly simple. Hope they give us a hard one before the day's over. All right, next one. An elevator. So we've got an 800 kilogram elevator moving downwards at 10 meters per second, and it's coming to a stop. So an elevators, they have the wires at the top, so there's going to be a tension in this thing. So we're going to have tension pulling up in that wire. This whole thing is 800 kilograms. I lost my problem. This one. 800 kilograms. It's moving downwards. This is going to be a one-dimensional problem in the y direction. I'm going to call that way up and that way down. So its initial velocity in the y direction is equal to negative 10 meters per second. Right?
By negative 10.
I'm calling that way down, that way up. The elevator is moving down at 10 meters per second.
Yeah, but why not just start at 0?
I can't choose the velocity to be 0.
Yeah, not the velocity, but your initial velocity.
The initial velocity is the velocity at the start of our problem.
It's just moving down at a constant speed.
Yeah,
So pick
it's
any-
not a constant speed. No, it's going to be slowing down. It's at 10 meters per second, it's going to come to a stop. There's going to be a tension in this. The elevator's coming to a stop. You get in the elevator, it's going down, and now it's stopping because it's coming to your floor.
Oh,
So there's going to be a tension in the cable pulling up, causing a deacceleration, causing the elevator to stop.
so velocity isn't constant.
No, velocity is not constant.
Okay. Okay, that makes sense.
So your initial velocity is 10 meters per second. Your final velocity is going to be 0 meters per second. You're coming to a stop.
Gotcha.
And let's see. It slows down with constant acceleration. And your displacement. So the elevator moves a distance of 25 meters in that time.
Okay.
Make sense? So if we call your y naught equal to 0, then we're going to call your final y equal to negative 25 because you went down 25 meters.
Isn't acceleration 25?
No, we don't know the acceleration.
Those two stop with being a constant. Oh, okay.
The acceleration over 25.0 meters. I mean, the units is a dead giveaway.
Okay, I see.
Meters is a distance. Okay, so Let's see, we just got calculate acceleration and then we use that to find the tension. So we're looking for the tension in this.
Okay.
Tension in the elevator cable. So first let's figure out how much the whole system is accelerating. Right?
Yep.
And then in this case, we're going to use that other equation. We're going to use v squared is equal to v naught squared plus 2a times our change in y. Final position minus initial position, that's going to be negative 25.
Oh, I see.
I don't know why I plugged in that number and not any other number. Let's plug in all our numbers. So 0 is equal to 100 plus 2a times negative 25. Right?
Yeah.
So what's our acceleration?
Negative 50.
Positive.
What? No, 2 times negative 25 is negative 50.
Okay, let me. 100 minus 50a. Okay. And that is equal to 0. What's a?
Oh, I see. So it's just 1/2.
You guys.
That's
Do a little bit of algebra. 0 is equal to 100 minus 50a.
Yeah, bring it over to the other side.
Okay, so 50a is equal to 100. What's that crazy a gotta be?
Oh, 2.
2. I need 2 50s to make that a 0. What's going on? 2 meters per second squared.
Yeah.
Okay, that's the acceleration of the whole system. So my force in the y direction, this is all happening in the y direction, is equal to tension minus weight, which is also equal to mass times acceleration. Free body diagram for the elevator. We have tension pulling it up, and we have its weight pulling it down.
Yeah.
Those are all the forces acting on it. And so the sum of those forces has to give us ma.
Yeah.
F equals ma, right?
Mm-hmm.
So I know that the force in the y direction, well, we're actually solving for tension here, so we can ignore that part of it, right?
Yeah.
Okay, so we're looking for tension. So what's tension? Tension is going to be m times a plus w. Let me rewrite w a little bit differently. mg.
Okay.
Good?
Yeah.
Factor out the m, and so t is equal to m times, I'm going to do g plus a in this case.
And what's M? Just 800 kilograms?
Yeah, it's just a mass. But here's how we could do it in any scenario, regardless of the acceleration. The acceleration in this case happened to be positive acceleration, so that makes the tension higher. If it were negative acceleration, that would make the tension lower. Anyways, so now we plug in and we figure out what the tension is. Sanity check. Is the tension greater than or less than the weight?
Less than.
it's greater. So
Greater than. Because we're causing the system to accelerate that way.
We're going that way?
No! We're
I thought
going down.
We're going this way, yeah.
Our acceleration is that way. We're stopping.
Oh, I see.
Okay.
Okay.
Good. So, whichever way our acceleration is, has to be the way that the sum of the forces is pointing.
That's right.
Okay.
Okay, so now we can actually get a number, 800 kilograms times 9.8 plus 2. And it comes out to 9440. Guess we can check it with the book, make sure we didn't make any mistakes. What is that part right now? 5.8? Oh, that was weird. 5.89440 newtons. Okay, that's exactly what we got. So we did right. Okay, next problem. Or I think we still use part of this problem for it. If I remember right, 5.8, 5.9. Okay, so now a 50 kilogram man stands on a scale inside the elevator inside this exact same elevator. So his mass was already adding to the mass of the elevator. So the elevator without him was 750 kilograms. Okay. He's in there with another 50. He's standing on a scale in the elevator.
Okay.
We want to know the reading on the scale.
That wouldn't just be his weight?
No, it wouldn't just be his weight. There's an acceleration. When you jump on the scale, does it show the same numbers when you just step on it?
No.
What happens? It spikes up.
Yeah.
Because that was a lot more weight. Because there's a much bigger force. Because it had to de-accelerate you.
Oh, I see.
Okay. So, for the free body diagram of the man, we have the normal force. This is how much the elevator is pushing up on him, or the scale that he's standing on, right? So, we got our scale right here. He's standing on the scale. And the scale is pushing up on him with the normal force. And his weight, we'll call it, meaning his weight due to the gravitational force of the Earth, is pulling him down, right?
Yeah.
Now, the force in the y direction is equal to the normal force minus his weight, which is equal to his mass times his acceleration.
Where's the normal force?
I mean,
oh, that's right.
it's how hard the scale is pushing on him. That's what we're looking for, the normal force. What does a scale measure? How hard it has to push you. That's what it measures.
Okay.
So, the normal force then is equal to ma plus w.
Or the
If
same.
Or
the same as before, right? mg.
Or the same as before, mg. So the normal force is equal to mass times g plus a. Same thing.
Okay.
Same equation. Why is it the same equation? Because the same way we calculate the normal force pushing on him is the exact same way that we calculate the tension in the top of that elevator. It's just different ways. Because the push from the scale ultimately comes from the tension in that cable. If I suddenly cut that cable and there's no longer any tension, the scale's no longer pushing on him because he's in free fall.
Yeah.
So all the push from the scale ultimately comes from that tension, which is why you calculate them in basically the same way. It's just different masses. Because while the tension does a whole elevator, the scale only has to worry about his weight. Anyways, so we do his mass, 50 times 9.8 plus 2, gives us 590. 590 newtons.
Yeah, that makes sense.
So, the scale is going to say 590 newtons. The scale normally says, when he's just, if he got it in this classroom, 490 newtons. So the scale is saying that he weighs another 100 newtons, or in other words, it's increasing his weight by a factor of 20%.
Isn't the elevator moving down though?
The elevator's moving down, but it's accelerating up. You feel accelerations, not velocities.
Yeah.
You have no difference between you just standing in this classroom like this versus you being in a rocket ship in the depths of space, traveling that way at a constant speed of 1 billion miles per hour. There's no way for you to detect that you're actually moving 1 billion miles per hour. If you throw up a ball, it comes right back down. If you throw up a ball and I start accelerating you that way really quick, it's going to come back and hit your face.
Yeah.
Okay. Was there another part to that? What does the scale say? That's it. That's all the scale says. And now notice, what about if the elevator, what about if he was weighing himself right as the elevator started moving down?
Then it would be less.
Then its weight would be less. So it's more when the elevator comes to a stop, it's less when the elevator starts moving.
Okay. Yes.
So in the end, it's all compensated for. There's no free lunch in physics. If you're getting something freeze one way, it's got to be somehow accounted for some other way. Okay. Now, oops, I erased those problems. But we have 3 more problems to do before we get on to friction. So problem 510. Let's see, you're sliding down a hill. We know the weight, we know the angle. So we'll start with that. So that's some angle alpha. So here you are on a hill, you're on a sled, sliding down a hill, having the time of your life, really enjoying it. Free body diagram for you. Let's do that over here. This is alpha, right here. And we know that you have a weight pointing downwards of W. And we know the angle alpha. There's no friction. We're looking for your acceleration. How much do you accelerate down that hill? Okay. So free body diagram on you, that's your weight. We've got the normal force pushing this way. Right?
Yeah.
And there's no friction. Notice that if we add these 2 vectors together, we end up with a vector that points this way some.
Which is supposed to happen, right?
Which is supposed to happen. Because you're accelerating down the hill.
Yeah.
Okay. So, let's see. What should we use for our XY? Should we switch it up a little bit this time? And put our XY like this? Oops. Well, yeah. So I'll call that my XY.
Okay.
So then, I'm going to draw my normal force very perpendicular, trying to draw that a little bit better. Perpendicular. My normal force, I need to break it up into its X and Y direction, right?
Yeah.
That's a right angle, and then this angle right here is going to be angle alpha. So in the X direction, oh no, I don't want a coordinate system like that. What am I doing? Because I want to find your acceleration down the hill. So I want to set it up so that my X points down the hill.
Okay.
Right? Makes sense? Easier way to think about it anyways, because then notice if we set up our XY like that, the normal force is completely in the Y direction. So it doesn't add any of your acceleration. So all your acceleration comes from your weight. Which helps our intuition, because you think, what if you were perfectly weightless in this scenario? You wouldn't fall down the hill.
Yeah.
Okay, so now we break this up into its X and Y components. Remember, always make the vector the hypotenuse. There's our right angle. This is going to be angle alpha. What's this side?
That's sine.
W sine of alpha. So I know that W sine of alpha is equal to that person's mass times their acceleration. Oops. Right? And I know that the normal force is equal to W cosine of alpha, right?
Yes.
Do we know their mass? Oh, we know their total weight. Okay, we know their total weight, so I don't think we're going to need this part. We know their total weight, so we do know their mass. What's their mass?
Just weight divided by 9.8.
W over G. So I know that W times sine of alpha is equal to W over G times A. Right?
Yep.
We're solving for acceleration. So acceleration then is just G times the sine of alpha. Move the G to the side, divide both sides by W.
Gotcha.
We good? Okay, sanity check really quick. What does this equation say? What if alpha were 0 degrees? What would my acceleration be?
Nothing.
What sign of 0? 0. So it says our acceleration would be 0. And obviously, if I lowered that alpha to 0, how fast would you slide down the hill? You wouldn't. There is no hill. Furthermore, what if I put that up at 90 degrees?
We just free fall.
Then you're just in free fall, and so your acceleration is just g, right?
Yeah.
And what happens when you plug in 90 degrees for sine?
You get 1.
You get 1. So a equals g times 1, or a equals g.
That makes sense. Okay.
Okay, so our answers make sense.
Yeah.
All right, next problem. We'll just skip 511 and go straight to 512. 511 is a contact one. Maybe we should do it actually. Shoot. Okay. You push a 1 kilogram food tray through a cafeteria line with a constant 9 Newton force. The tray pushes on a 0.5 kilogram carton of milk. The tray and the carton slide on a horizontal surface so greasy that friction can be neglected. Find the acceleration of the tray and carton and the horizontal force the tray exerts on the carton. Okay. So we've got our tray of food there, and we got our carton of milk here. The tray was how many kilograms? 1. So the tray is 1.00 kilograms. The carton of milk is 1/2 a kilogram, but with 3 significant figures. And we're pushing on it this way with a force F equal to
9 newtons.
9 newtons. So first thing we need to do is find the acceleration of the system. Second thing we want to find is how hard the carton is pushing on the milk.
Okay.
You with me?
Yeah.
Yeah.
Okay, so first off, let's find the acceleration of the whole system. Well, force equals mass times acceleration. So acceleration is just force divided by mass. So what's our acceleration in this case?
9 divided by 1.5.
What's 9 divided by 1.5?
4.
4?
No. 6.
6?
6.
Yeah.
6. 6 meters per second squared. Okay, so there's our acceleration of the whole system. Now, I want to know how hard is this pushing on this? You with me?
Mm-hmm.
What do you mean how hard?
Notice that from the milk carton's perspective, all it knows is it's being pushed by this tray. It has no clue about you pushing the tray.
Okay.
So how hard is the tray pushing the milk carton? What's the force of the tray on the milk carton equal to?
Wouldn't that just be 9 newtons?
No, it's going to be equal to its mass times its acceleration. What's the mass of the carton of milk?
1/2.
1/2. What's its acceleration?
6.
So what's the force on it?
3.
3 newtons.
Oh, I see.
So notice you're pushing with 9 newtons, and you can think about it as 6 newtons are going towards pushing this thing, and 3 newtons are going towards pushing this thing.
Oh, that makes
That's
sense.
one way you can think about it. You can draw the free body diagram for this thing now. Let's do that really quick. For the tray. For the tray, we know that it's being pushed this way with 9 newtons. Right? By you.
Mm-hmm.
We also know it's being pushed now this way by the carton of milk, the same hard as it's pushing on the carton of milk, so 3 newtons. So what's the total force on the tray?
6 newtons.
6 newtons. 6 newtons. It has 1 kilogram mass, so it better be accelerating 6 meters per second.
Wait, the total or the net?
The net. Total, net, same thing. Add them all up. That's what we mean by total.
Okay.
Remember, they're vectors.
Yeah.
So it's like asking what's the total of 9 and negative 3.
Okay.
Okay. So there's one with some contact forces in between. Finally, the last one, we got a glider on an air track with 2 weights. we'll set the picture and then see what we're trying to figure out. Just so you know, the word glider is going to come up a lot when you read a problem. We don't mean like a hang glider. A glider is, the way it works is we've got a metal V like this, metal V like that, and it's a sheet of stuff, and it has a bunch of holes in it. So tons of holes all over in it. And basically what you do is you blow air inside of that thing, so it pushes air outside of those holes. And so a glider is just something that sits on it, and the air holds it up, and it creates almost a frictionless weight. So that's one of the ways we set up like a frictionless system.
Oh, I see.
It's kind of like how an air hockey table works. Similar idea.
Gotcha. So it's kind of like everything just floating.
Yeah, that's what air hockey's trying to do. Make so it's floating just a little bit, and that way it's almost frictionless, an air hockey puck. You turn off the air and suddenly that puck is sticking.
Yeah.
Same concept, but gliders meant to be more precise. It's meant for lab stuff. Anyways, so we've got now this mass moving along a glider, M1, so it's frictionless. It's going over to a pulley here. Better. It's coming over and then down from a pulley, and it's on some table. Well, just going to attach the pulley to the table. Table comes like that, then we got the legs of the table, whatever. Put that in so they don't get confused since I'm making a mess. Okay, so we got the mass sliding on a table, and it's attached to some other mass, M2, down here.
Okay.
Frictionless. There's no friction. So no matter what M2 is, this is definitely going to slide that way.
Yeah.
Okay. So we've got M1 moving on a level frictionless air track in a physics lab. The glider is connected to a lab weight M2, non-stretching weightless string, frictionless pulley. Find the acceleration of each body and the tension in the string. Okay, so find the acceleration of the bodies and then the tension in the string. So let's start with the acceleration of the bodies. Now notice that this is still a one-dimensional problem, as unintuitive as that seems, because it's going this way. It's all happening in this direction.
Gotcha.
Pulleys make us think that one-dimensional problems are really two-dimensional problems. But pulleys just maintain the same forces and changes the direction of our picture. But this is still just a one-dimensional problem.
Okay.
Make sense?
Mm-hmm.
Okay. So, obviously we're going to have some tension pulling here. We're going to have that same tension pulling here since it's a weightless string. And we're going to have, right here, we're going to have W2, the weight of 2 pulling down. Right?
How about the weight of M1?
Doesn't factor into it.
We don't take it into account?
Well, it has its weight and then you have the normal force. So
Oh,
it
which
has its
adds
weight
up to
and it
zero.
has a normal force, which goes at 0.
Okay.
So in the direction of motion, these are all the forces at play.
Gotcha.
You with me?
Mm-hmm.
Okay. So now I know that the sum of the forces, I know that the mass times the acceleration of the system, M1 plus M2 times the acceleration of the system, is equal to what? What force is responsible for all the acceleration of the system?
The weight.
Just this weight right here. If I were to add up that tension, and that weight, I'd be left with just that weight, because those tensions again perfectly cancel out.
Yeah.
Oh, I see.
Simpler way to think about it is, what's causing all the movement in the system? The weight of that.
Yeah.
So basic intuition is always useful here. So now, what's the acceleration then? Right?
Yeah.
Okay.
Which is equal to right?
Okay.
If we want to write it that way.
So it's just G over M1?
No, because it's an added denominator.
It's a what? Oh, definitely not G over M1. Sorry, I didn't process what he said. No, definitely not. This is 100% not even remotely close to this.
Is that because of the constant multiplies?
You can only multiply by 1 and add 0. You need to rewrite this as multiplying by M2 over M2. So you'd have to factor in M2 out of the bottom,
Oh, I see.
which you cannot do. So no, very, very bad. Someone should teach you some algebra. Okay, so that's the acceleration. Now we need to find the tension. Right?
Yeah.
Now, I know that just focusing on this mass now,
Okay.
doesn't really matter which one we focus on. We can focus on that one if we want. We can focus on this one if we want. Not sure which one will be easier. We can focus on this one. Okay. I know that this thing, the net forces acting on this, are what? Acceleration times m1. Right?
Forces acting on it?
The net forces acting on this thing, the sum of all the forces acting on this, give us its acceleration times its mass.
Yeah.
But what about the weight acting on it?
Add up all the forces acting on it. Everything. When you add them all up, you get the acceleration times its mass. F equals ma.
Okay.
Newton's second law.
Yeah.
Okay. Now the only force acting on it, well, there's 3 forces acting on it. You have the normal force, you have gravity, those 2 cancel out, so we won't worry about them. And then tension. So this is also equal to the tension in the string.
Okay.
So that's the tension. So tension is equal to m1 times A. So if we follow this equation, it's m1 times m2 times g all over m1 plus m2. With me?
Yeah.
There's the tension. Here's the acceleration.
Okay.
Okay? Let's go through some thought experiments. Let's really quick think what happens if we take the limit as m1 approaches 0. What happens to the acceleration?
It's closer to
Look at this one. If m1 gets closer and closer to 0, what does the acceleration get closer and closer to?
0.
gravity.
If m1 goes to 0, what's the denominator then?
Oh, just M2 and, okay. So yeah, just gravity.
Just g. Which, look at our picture, makes perfect sense. If that doesn't have any weight at all, then that just falls down with the force of gravity.
Oh, yeah.
Okay? And what does the tension equal as m1 approaches 0?
But there is no tension.
0. Perfect. This is a free fall, there's nothing pulling up on it.
Yeah.
Make sense?
Yeah.
Another sanity check. Let's think about the limit as m2 approaches 0. What's the acceleration?
That's getting closer to 0.
0. So if this weight becomes weightless, there's nothing pulling this that way anymore. Make sense? And what's the tension still?
0.
0. Because if this doesn't have any weight, there's nothing to create the tension to begin with.
Yeah.
Make sense?
Yep.
Nice little sanity checks. Make sure the math makes sense, the equations we're working with make sense. Okay. It's taking way too long to get through these problems. Okay, that's 5. That's the first 11. Now we need to cover some new material.
That's the problem.
Yep, that was a problem. Find the acceleration, the tension. That's all we were supposed to do. I just wanted to point out that other stuff to show you, keep you thinking about how the math makes sense. Okay. Now, some of the little bit of new material we'll be talking about today is friction. We've had a little bit to say about friction, but not a lot to say about friction. Ultimately, in most cases, what's going on with friction? Why is it that if I start pushing this chair, it doesn't instantly slide? You say friction, but what's physically causing friction? How do you explain that to a little kid? What's going on?
The ground is stopping.
It's holding on.
Holding on, there's like things grabbing?
Yep.
Yep. Reaching out and really contracting those muscles? What's going on? What's going on is, no matter how perfectly smooth the surfaces that we're talking about, when you zoom in really close, those surfaces are jaggedy. And they're on top of some jaggedy surface, right? Okay.
Yeah.
And so when you try to push this thing, it's making contact with little pieces sticking up all over the place, sticking out, like the ground. And so it's hard to get it to start moving. You got to push it and get it out of all those little wedges. And that's what happens when you start it moving. Make sense?
Okay.
And then you get it out, you keep sliding it along. Once you stop, it's going to resettle into those positions. You have to keep pushing it to stop it from falling into those positions.
Why does it affect it more when it's heavier, or does it?
Why does it affect it more when it's heavier? Because then how much is being pulled down into those wedges is increased. Weight does change how much friction it experiences.
Isn't that canceled by the normal force?
Sure, it's canceled by the normal force when you're thinking about the net force on it isn't causing it to move, but there's still that weight pushing down, and it's still, I mean, let's lay you down on the floor and then have an elephant stand on you. Yes, the net force on the elephant is 0.
Okay.
But you and the elephant are a lot closer than if I put a piece of paper on you. The net force between you is still 0.
Yeah.
So there's a lot more pressure down, and it shoves down into it further. And it can do more like actual deformation on that thing, cause it to bend. So ultimately, why is there friction? Oversimplified, because surfaces are bumpy. They're not perfectly smooth. And even if they were perfectly smooth, you also can have molecular interactions between things. Even chemistry can come and start taking a play in terms of friction. Like water sticking to water. Have you ever noticed how you can take a cup of water and you can fill it up above the brim and the water doesn't spill out?
Yep.
That's chemistry now coming into play. The water sticks to itself. And so it has to do with what goes on chemically with those things, and also the fact that there's no such thing as a perfectly smooth surface. Those two things together are pretty much what's responsible for friction, physically speaking. Make sense? Now, obviously, we're not going to talk about friction on such a small, minute level. We need to talk about it in a simpler way, like the friction of just sliding a box across the carpet. Those are the types of problems we're going to be interested in, right?
Okay.
So, friction in that case, what does it roughly look like? Well, there's two types of friction. There's kinetic friction and then there's static friction. Kinetic friction is friction with motion. Static friction is friction without motion. Right now I'm pushing on this bookshelf and it's not going anywhere. Why isn't it going anywhere? Friction. But it's because of static friction. So static friction is a friction when there is no motion. Kinetic friction is a friction when there is motion. If I'm sliding a box, the friction is kinetic friction. If I'm just pushing on this, it's static friction. For the purposes of this class, kinetic friction will always be a constant. I don't know, we might get problems where it's not, but initially, kinetic friction is always a constant. In other words, if I start sliding a box with a constant velocity, kinetic friction is always against me at a constant number, we'll say like 100 newtons, something like that. You with me?
Yeah.
Static friction is different. If I push on this with a force of 1 newton, what's the force of static friction? 1 newton. If I push on it with 10 newtons, what's the static friction? If I push on it with 100, what's static friction?
100.
And so it changes. So static friction is any number from 0 to some max value, whereas kinetic friction is always a constant. Make sense?
Can you go from static to kinetic?
You always go from static to kinetic. Before I can get a box moved, I first got to start pushing a box and get it moving. So it's static, static, static until the box starts sliding. Then it switched to kinetic.
I see.
Okay. So kinetic friction. How do we calculate kinetic friction? It's equal to some constant, mu sub k, that's a Greek word mu, So static friction is equal to some constant. That constant depends on the materials we're talking about. It's a lot easier to push a box on ice than it is to push a box on really thick carpet. Times the normal force. How much it weighs. The more it weighs, the harder it is to push.
Yeah.
Make sense?
Okay.
Now this just gives us the magnitude. The magnitude of kinetic friction is this. Kinetic friction always opposes the direction of motion.
Okay.
So it's almost always perpendicular to the normal force. So this is not a vector equation, this is just giving you the magnitude of the vectors.
Yeah.
Okay, so making to a sense of it. What does it depend on? It depends on the material, that makes sense, and it depends on the weight. That makes sense. That coincides with our day-to-day experience. Right? And then, always opposite direction of motion, we said that. Okay, static friction is different. Static friction is always less than or equal to some max value.
Less than or equal?
Yes.
Okay.
Notice right now, static friction is 1. Now it's 10. Now it's 100. And static friction kept increasing in that case. So static friction is always going to be between 0 and some max value. Whereas kinetic friction is always a constant.
Okay.
Okay? So it varies from 0 to some max value. So now, set up an experiment. We're not going to do the experiment, but here would be the results of the experiment if we set this up. We're going to take some block on some surface like wood, something like that, some heavy block, and we attach a rope to it, and we're going to pull on that rope. And we're going to pull on that rope until we get the box moving. So I'm going to grab the rope, and I'm going to slowly increase the tension on it. So it's going to start at 0 tension. I'm going to slowly start pulling harder and harder and harder until I finally get the box sliding. Make sense?
Mm-hmm.
And we're going to pretend that there's some sort of measuring device on this rope that can measure the tension in the rope.
Okay.
So here's what that would measure. It would measure initially the tension 0 when I'm not pulling the rope. I start pulling, and finally the box starts sliding. And suddenly the tension in the rope drops. And as I'm sliding that box along the floor, the tension looks like this. Wiggling, but roughly constant.
Okay.
So this height right here, the point that we had to reach to get that box to start moving, that is mu sub s times n. That's what we mean by the max value that static friction can be.
Oh, I see.
And then this squiggly line, kind of what that is averaging out to, we call kinetic friction. The height that that reaches. So that's static friction and kinetic friction. Make sense? And then the book has a table of a bunch of values for a bunch of different materials. I don't know if they'll ask you to find how much force you need to accelerate one material on top of another material, but they have a table for what these constants are for a bunch of different materials. So for example, for steel, if you're talking about on steel, mu sub s is 0.74 and mu sub k is like 0.5 or something like that in these equations. Okay, talk about that. Okay, on now to just tell more examples. Love it. I don't know how many of these I can do. We'll start doing every other one now.
Okay.
Okay, this one. You want to move a 500 Newton crate across to level 4. To start the crate moving, you have to pull with 230 Newtons horizontally. So start recording some values here. Where's my eraser? Bring it over. So let's see. I know the weight was 500 Newtons. And I know the force that we're going to pull with, I think they said 230 Newtons. Yeah, 230. Once the crate breaks loose, it starts to move. You keep it moving with a constant velocity of only 200 Newtons. Okay, so force to break static friction was that, and then force to break kinetic friction was 200 newtons. Okay, so it's saying I'm pushing a 500, let's draw a picture. Here I am pushing some big old crate that has a weight of 500 newtons. I have to push it with 230 newtons to get to start moving, and then I only have to push it with 200 newtons to keep it moving after that.
Okay.
And this is probably pretty intuitive for you as well. If you've moved a lot of boxes or fridges or stuff like that in your life, it's hard to get to start moving than to keep it moving. Once you get moving, you say, no, don't stop, keep pushing. Yeah. Which comes from this fact right here.
Okay.
Anyways, so now our job is to calculate mu sub s and mu sub k. I think. Let's double check. You do that, you do that. What are the coefficients of static and kinetic friction? Okay, yeah. So we're trying to calculate mu sub k and mu sub s. Right? So the weight of this box, free body diagram, we're going to have the normal force pushing up, we're going to have the weight pushing down, and then we're going to have the force we're pushing with pushing that way, and then we're going to have the force of friction pushing that way. Right?
Yeah.
Okay. So the important point is that the normal force has the exact same magnitude as the weight. Okay. So now let's start with static friction. So I know the force that I apply to break static friction is equal to 230 newtons, but that's also equal to static friction.
So.
Huh?
Okay.
Make sense? And how do we calculate static friction?
Mu sub s times normal force.
Mu sub s times the magnitude of the normal force.
Okay.
So now we need to calculate mu sub s. Let's get rid of the 230 for a second. Let's just say that's equal to that's equal to that. So mu sub s then is what? It's just the force we had to push with
Over the normal force.
over the normal force. Similarly, mu sub k is going to be calculated in the exact same way. It's going to be the force that we had to use to break kinetic friction over the normal force, right?
Okay.
Kinetic friction.
To overcome kinetic friction, sorry.
Why do you say overcome instead of something like keep it going?
So we're pushing it with just enough force that we're overcoming kinetic friction so we can keep it moving. Because if kinetic friction overcomes us, then it's going to slow down and stop.
So that's moving at like a speed of 1.
Constant speed, doesn't matter what it is. It's just as hard to keep it going 10 meters per second as it is to keep it going 1 meter per second in terms of force. You'll do more work if you make it go faster, and you'll get tired quicker. You're aware of. Well aware of. Wow, that was weird.
So if you go slow, you're doing the same amount of work.
No,
If you go fast.
you're pushing with the same force. You're doing more work if you go fast, but you're pushing with the same force in both cases.
But you get tired faster going fast.
That's because you do more work.
So do you end up with the same outcome?
Now, if I push a box really fast for a second versus pushing it really slow for a second, in the really fast scenario, I got a lot further.
Well, yeah.
Oh, you're saying if the box ends up in the same position,
Mm-hmm.
then you do the same amount of work in both cases. Whether you do it fast or slow, same amount of work. You can't save work by doing it faster. The work it's going to take is the work it's going to take. You can't trick physics.
I guess we'll see that tomorrow.
Okay, anyways, so what's this equal to?
It's equal to
Now plugging in actual numbers.
230 over 500.
Yeah, 23 over 50.
50.
230 over 500. 23 over 50. I just cancel out 0.
Okay.
Okay. And this one is equal to
2
over 5.
2/5. And let's just think about the units for a second. What are the units going to be? We have a force over a force.
So it's still just newtons.
So it's just a factor. It's not a Newton. No. We have newtons in the top, newtons in the bottom. Those cancel out.
Oh,
So it's
because,
just a number.
well, it's a constant, yeah.
So these are just constants, they're just numbers. They
Okay.
do not have units. Make sense?
Yeah.
Okay. So we'll skip that example and go to the next one. Pulling at an angle, okay. In example 5.13, we're not gonna let's get around it. Oh, 5.13 is the one we just did. Okay.
Yes.
So in example 5.13, suppose you move the crate by pulling upwards on the rope at an angle of 30 degrees above the horizontal. How hard must you pull to keep it moving with constant velocity? Assume mu sub k is equal to 0.4, which is what we calculated. So we have the same mu sub k. We are going to ignore static friction in this case. A little bit different scenario. So we've got the big block right here. Then we've got the rope like that at an angle of 30 degrees. And you are pulling the rope.
So that would kind of be like having a rope over your shoulder.
Yeah, that's actually how they drew it. I just didn't want to try and draw that. So, we know that mu sub k is 0.4 is what they said, 2/5, same thing, right? Our job is to calculate how hard do we have to pull to keep this thing moving with a constant acceleration. And it's the same box. Oh shoot, we erased the weight of the box. I think it's 500 newtons, right?
Yep.
Weight is equal to 500 newtons. Okay. So, free body diagram for this box, really quick. We're going to have our force pulling this way. We're going to have its weight pulling this way. We're going to have the force of kinetic friction pulling this way. And we're going to have the normal force pulling this way.
So it's just what? Cosine of 30 degrees?
This right here is 30 degrees. So let's add up our forces in the x and y direction. Put a note over here. We know that mu sub k, in case we forget, is equal to 2/5. So our forces in the x direction add up to what?
Just
0.
Zero.
Moving with constant velocity. Right?
Why is that?
the force is add up to 0. Gotcha.
The forces add up to 0. The box is moving with constant velocity. It's not speeding up, it's not slowing down.
Okay.
Why?
If there's a net force, there's an acceleration. There's no acceleration. So there's no net force.
But if there's no, if all the net force is 0, doesn't mean just staying still?
No. It just means you're not accelerating. You and I in outer space. You're floating that way from my reference frame. From your reference frame, I'm floating that way. The net forces on us are obviously 0,
Yeah.
and yet we're moving.
Okay.
Okay. So, force implies an acceleration. If you have a force, you have an acceleration. If you don't have an acceleration, then you don't have a force. Right?
Yep.
Okay. So, the sum of all the forces in the x direction adds up to
0.
0. And what are the forces in the x direction? If we call that one positive and that one negative, we have F times cosine of 30 degrees minus F sub k.
Okay.
Or in other words, we know that F sub k, and that's equal to 0. In other words, we know F sub k is equal to F times cosine of 30 degrees. With me?
Yep.
In the y direction, if we have all the forces in the y direction, we get
0.
0, and we can write it as it's going to be the normal force minus, the normal force plus this is also pulling up, right?
So sine.
So the normal force plus F times the sine of 30 degrees minus W is equal to 0. Or in other words, we probably want to solve for the normal force in this case. So the normal force is equal to the weight minus F times sine of 30 degrees.
What are
Agree
we
on that?
looking for again?
we're looking for mu F sub k. Is that
So
what
do
we're
you
looking for?
even need the second part?
I don't know.
I don't
Oh
think
no,
you need to know the
sorry.
second.
We're trying to figure out how hard you have to pull. That's what we're trying to figure out.
So the total force.
We're trying to figure out, no, the force, how hard you pull on the box to get moving. It's not the total force.
I meant your force in your x and your force in your y.
No. Your total force in the y direction is going to be 0. Your force in the y direction is not 0. The box does not accelerate in the y direction.
Yeah, you're looking for your force, right?
Notice that you have a y component to force,
Exactly.
but the box doesn't.
Okay.
We are looking for the force that you exert on the box. We're not calculating the net force on the box. We already know net force on the box is 0.
Yeah, I'm saying all you're trying to find is f of y and f of x.
Oh. Yeah, I should have called that F. Let's call this F of U.
Okay.
F of Y as in F of U.
Right.
That's what we're trying to find. F of X here, I just meant the sum of all the X forces on the box.
On the box.
And this was the sum of all the Y forces on the box.
But that's how you find how much force you're putting on.
We're looking for F sub Y. So let me put the Y's in there. F sub Y, F sub Y, F sub Y, F sub Y. That's what we're looking for.
You might want to change your f of sub y for the total one.
'Cause you
Oops.
do-
What was that? Oh, son of a gun. Can't use Y.
Yeah.
Gotta use you.
F of U. Okay. F sub Y. U. Okay, yes, these are not related.
Okay, that makes more sense.
Alright. So we're looking for F sub U. Okay. So I know from this equation that F sub U, right over here, F sub U is equal to F of K divided by cosine of 30. What's cosine of 30 degrees?
It's just root 3 over 2,
Yeah, that's root 3 over 2.
right?
Guess again.
What? Cosine
Cosine of 30 degrees.
cosine of 60 degrees is 1 half.
Are we further in the x direction at 30 degrees or? Oh, you're right. I was measuring from the top. It's a program I'm working on, and I have to do it that way. Sorry. You are right. Root 3 over 2, or in other words, 2 root 3 over 3. Because we're dividing by it.
Yeah.
Wouldn't that just be 3f of sub k over?
So we're doing, it's f of sub k, I won't do the jump like I did last time. 2 over root 3. Just leave it like that now.
Okay.
Good?
Yeah.
But now what is f sub k equal to?
So, okay.
F sub k is equal to mu sub k, which is 2/5,
Times 500.
times the normal force, not the weight.
Isn't the normal force 500?
No. Here's the normal force. It's 500 minus how hard you're pulling up. Because notice that you're lifting some of the weight.
Oh.
So the
yeah.
normal force doesn't have to do that much work anymore. It's like if you were standing on Jeremy and I was pushing up on you some, you feel lighter to Jeremy now. The normal force on you from Jeremy is less.
Gotcha.
So, times our normal force times n. Right?
Yeah.
So that's going to be, geez, that's getting ugly. Is there a smarter way to do this I'm just not seeing? Alright, we'll just try it out. So our normal force then is W. W minus F.
You could substitute that.
let me keep all the trig functions in here, because I think some of those are going to end up being kind of nice. And canceling out. So let's restart right from here. Let's just write out what I know. I know f sub u times cosine of 30 degrees is equal to mu sub k times our normal force. And our normal force is W minus f sub u times sine of 30 degrees. Did I do all that right?
Yeah.
Okay, so we say f sub u times cosine 30 degrees is equal to mu sub k times W minus mu sub k times f of u times sine of 30 degrees. Move this to the other side and factor out the f sub u. So we're going to get f sub u times cosine of 30 degrees. Okay, those aren't canceling out like I thought. Plus mu sub k times sine of 30 degrees is equal to mu sub k times W, right?
Yeah.
I move this term to the other side and then just factor out the f sub u. And so finally, f sub u is equal to mu sub k times W all over cosine of 30 degrees plus mu sub k times sine of 30 degrees. Good? Let's check that. Mu sub k times W all over cosine of 30 degrees plus mu sub k times sine of 30 degrees. Yep, that's exactly what we did. And if you plug it all in your calculator, it comes out 188 newtons. We'll trust the book on that one. Rather than plug it in. Good?
Yeah.
Okay. Next one. Oh, they used T. Should have done that. T for tension in the rope. That would have been better. Ooh, I really want to have that conversation, but I don't know if we have time to have that conversation. Just skip it and come back if we have time. All right. Forces with circular motion.
Circular motion.
Circular motion. You remember talking about uniform circular motion?
Yep.
Uniform circular motion, and we calculated what the acceleration is in uniform circular motion. A couple times. We did two different ways, right? We said, one way we said it is that your acceleration vector is equal to omega squared times the negative of your position vector.
Yeah.
And so in terms of magnitude, it was just A is equal to omega squared times R.
Yeah.
And then if you want to convert that to velocities, you need to remember that. How do I convert omega to velocity?
Degree.
No, you just multiply by R.
Oh.
If I know that I'm going around the circle, if I have an angular speed of 2 radians per second, so I'm going around the circle once per second, and the circle has a radius of 5 meters, what's my velocity?
10 meters.
10 pi meters per second.
10 pi meters.
So to get from your angular speed to your velocity, you just multiply by R. So remember that velocity is equal to omega times R, right?
Yeah.
So another way that we could write this, in other words, omega is velocity over R, so we could also write this as v squared over R. Same thing.
Yeah.
See that?
Yeah.
From this, I knew that omega was equal to v over R. So I did that substitution here. That's where my v squared comes from, and then it was over R squared, but when R cancels out. Good? Okay, and then the other way that we could calculate this acceleration was in terms of the period. Equation I don't ever really use, but the author has it there, so we'll write that one as well. So notice that your angular speed is equal to, how do you calculate angular speed? You take how many radians you went divided by how long it took you to go that many radians.
Yeah.
Right? So you say going a full circle divided by the time it takes you to go around the full circle. The period. Period is the time it takes to go around the circle once. Right?
Yep.
So omega is also 2 pi going around the whole circle divided by how long it takes to go around the whole circle. So we have that this is also equal to, if I replace omega with this instead, then we would have gotten 4 pi squared r over t squared.
Oh yeah.
So these are the 3 ways that we can calculate your radial acceleration. Good? Quick refresher there. And that's all they discussed there, blah, blah, blah. Okay, so let's do a problem now. A sled with a mass of 25 kilograms rests on a horizontal sheet of essentially frictionless ice. It is attached by a 5-meter rope to a post. Once given a push, the sled revolves uniformly in a circle around the post. If the sled makes 5 complete revolutions every minute, omega is equal to 5 revolutions per 1 minute. We'll convert that in a second. Find the force exerted by the rope. So what does tension equal in the rope? Okay, so I'll set up our picture now so that you understand what's going on. So we've got a pole dug into the ice. We're looking down from a bird's eye view. Here's a pole dug down into a sheet of ice.
Okay.
And there's a rope attached to the pole, and also attached to a sled. The rope is 5 meters. You come along and you push the sled that way, and then you walk away. The sled's on a perfectly frictionless surface. So the pole's stuck into the ground, so the sled's going to go around in a circle like this, over and over and over again.
Okay.
You with me? Our job is to find the tension in the rope, because there's going to be a tension pulling it that way. Right?
Yeah.
Okay. Oh, that's why they didn't use T, because T is a period. Okay, so find the force in the rope. That's what we're after. Good? Now, what is the force in the rope? Obviously, it's going to be mass times acceleration. In this case, we're talking about centripetal acceleration. It's the only acceleration we have.
Centripetal?
Centripetal. The acceleration due to it turning. Radial, I guess. Radial, centripetal, same thing. I might accidentally switch how I say those.
Yeah.
Centripetal is what it was called when I took the class, so that's what's in my brain.
Yeah.
Anyways, so it has that acceleration this way, causing it to move. Causing it to turn, I mean. So it has constant velocity, its velocity doesn't change. It does have an acceleration, but the acceleration is just going into turning it. No acceleration is going into speeding it up or slowing it down.
Okay.
Make sense?
Yeah.
Okay, so what is the force then? So the force is equal to the mass, 25, times our centripetal acceleration. So now we got to figure out what ACP is, and then we're basically done. And we can use whichever of these equations we want. But first, let's get omega into radians per second.
All right.
Radians per second.
Yeah, you always want your omega in radians per second.
So it makes what, 10 pi per minute?
Over 60.
Oops, this is omega.
Oh yeah.
And that's now radians per second. So always get your omega in radians per second. Otherwise, your answers will go all over the place. Okay, so now that we have omega as 10 pi radians per second, we can just plug that in to this equation to find centripetal force. right?
Yeah.
Okay.
So force is equal to mass times acceleration. And it's going to be, squaring this, we're going to get 100 pi squared over 3,600 times 5, the radius.
So 500 pi over that.
Yeah, 500 pi over that is one way you can think about it. 100 cancels out with that, so F is going to be equal to, the 100s go out, 5, bring that over here with the 25 here, so 125 pi squared over 36.
Oh, yeah, that's pretty simple.
Then get our approximation. See if they give it to us easy enough, see if we can actually check our answer. Oh, that was just the acceleration. Okay. They did a slightly different way. They rounded their acceleration first, like you shouldn't do. So just calculate it. So 125 times pi squared divided by 36, 34.3, 34.3. So we got the same thing, 34.3 newtons.
And that's the tension on the.
That's the tension in the rope. Imagine you were on the sled holding the rope. Notice that you have to pull with a force to stay on the circular path. Yeah.
Okay.
If you let go of the rope, then you suddenly take off in a straight line that way.
Yeah.
Because now there's no longer that force causing you to turn. So you're just moving in a straight line with constant velocity. Okay. 519, 520. Should we skip that one and just. That one's kind of the same as 522. We'll just go all the way to do 522 and 523. So just two more. I think those will capture the most useful of them. Okay, so there's a centripetal acceleration to keep you moving in a perfect circle, right? You need centripetal acceleration.
Okay.
So the next one we're going to do is actually a pretty cool one. We are going to calculate how much we need to create a bank. You probably noticed that on roads where it turns, the road actually slants like that. Yeah. So we are going to create a road here that slants at some angle alpha. And it's slanting from a bird's eye view when we look at the road. The road is going like this, around some path. This is looking at the road head on, so the car drives on top of the road. Here's the top of the road.
Gotcha.
And this is from a bird's eye view. Make sense? And so it's going to be turning some quarter of radius r. So putting r into our picture, r like going from the center of the road out to some point, r is right there. You with me so far?
Yeah.
Okay. So I'm not sure exactly what the problem is yet, but it's going to do something like that. So for a car traveling at a certain speed, it is possible to bank a curve at just the right angle so that no friction at all is needed to maintain the car's turning radius. Then a car can safely round the curve even on wet ice. Your engineering firm plans to rebuild a curve in example 5.21. Crap. So that a car moving at a chosen speed v can safely make the turn with no friction. What angle alpha should we use? So we're given the velocity v. We need to find the angle alpha we need to apply here for where the radius is. Go to the previous problem. Oh, just with radius r. It doesn't tell us what the numbers are. But so we know the velocity that cars typically travel on this road. That's just v. We know the radius of this turn. That's just r. So those two are given to us. Our job is to try and calculate alpha.
Find the angle.
We're trying to pick the angle that we should build this road at so that there is no friction required for the car to make the turn. Make sense? Because, yeah, like I said, there could be wet ice on the road. You don't want anytime there's wet ice for a car to suddenly take off the road. You want the road to keep the car on the road as much as possible. So, free body diagram now for the car. Guess we'll just kind of draw it right here. Come up this way some. So what do we have acting on the car? We have the normal force pushing the car up this way, right? Mm-hmm. And we have the weight of the car pulling the car down. And that's all we have. Now we want to calculate these angles so that it creates a force this way necessary for the centripetal force. So we want these two vectors to add together so that the net result is to create a force that way, which is just enough force to turn the car.
Okay.
Does that make sense?
Yeah.
So I want this normal force to cancel out that. I want the normal force in this direction to perfectly cancel out the weight and have enough left over right there to push the car that way to keep it turning at just the right amount.
So you want, oh, I see.
So, I kind of didn't draw my arrows very good. I want the normal force to be bigger than the weight. Try to make that clear. No, I exaggerated too much. So there's our normal force. This right here is, if this is alpha, this right here is alpha. So this right here is going to be n times cosine of alpha. And this right here is going to be n times sine of alpha. Right? And I want n, and I want it so that n times sine of alpha is equal to the mass of the car times its centripetal acceleration times v squared over r.
Wait, can you go over that? N times sine.
So this component of the normal force completely cancels out this weight,
Yeah, I got it.
leaving us with just this, n sine of alpha.
Okay.
And I want n sine of alpha, this force right here, to be exactly the amount of force I need to turn that car around the curve. Back to the bird's eye view. If a car is driving along here, and it's turning around this arc of radius r, it needs to have an acceleration equal to v squared over r to keep it turning on this arc. If we get rid of that acceleration, it goes off in a straight line.
Okay.
Right? So I want the car's mass times its acceleration. I want the force on the car. I need to supply a force on the car. That's what this is going to do. This is my force on the car.
So that's what we're finding, the force on the car?
We're trying to find the alpha I need to produce this acceleration.
Which is the force on the car.
So we know the velocity, we know the radius. Our job is to find the angle for that velocity and radius, because it changes, right?
Yeah.
So on some part of the highway, it might be a part where you have a kind of a sharp turn, and the speed limit might be 55 miles per hour. And so that's why we'd use in that case.
I see.
Make sense? Okay, so the normal force times sine of alpha is equal to that. Now I also know that the normal force, right, this other equation, I also know that n times cosine of alpha is equal to the weight. I wonder if that's going to help me. It's equal to m, the mass of the car times g. Hopefully those masses come out somehow. With me so far?
Yeah.
So I'm going to solve for n in this equation and plug it in up here.
I see. Okay.
So n here is equal to mg over cosine of alpha. Now I'm going to plug that in up here and rewrite this equation over here. So I'm going to get mg sine of alpha over cosine of alpha is tangent of alpha. So I have mg tangent of alpha. That's this. That's this times sine of alpha. Is equal to m times v squared over r. Good with that substitution?
Yep.
Beautiful, the masses cancel out, so you don't need to know the mass of the car.
Okay.
So, g times tangent of alpha is equal to v squared over r. Or tangent of alpha is equal to v squared over r times g. Let's make intuitive sense out of this. Now tangent gets bigger as alpha gets bigger. So the bigger the angle, the bigger the tangent of the angle, right? Mm-hmm. So we're saying if the velocity gets faster, the angle has to be bigger. That appeals to our intuition, right?
Yeah.
And it also says if we make the radius bigger, we can make the angle smaller. If I have a really big radius, then you can take the turn really slowly.
Yeah.
Okay.
Does that make sense?
Mm-hmm.
And then furthermore it says if gravity is stronger, then we don't need as much of an angle.
So you don't even need to know what the car weighs.
Nope. Car's weight has nothing to do with it. Isn't that crazy?
How does that work? Wouldn't
Just
the mass of
cancel
the
out.
car, like wouldn't a
Big truck.
very heavy car like a Tesla versus, I don't know, a 1996 truck have two different things to do with it?
Nope. We just showed it.
Yeah, the math makes sense, but I mean, how
And
does
it's
that
because you had a mass over here. Your mass, let's see the two ways to say this. Your mass helps supply the force that pushes you this way.
Okay.
Because it's the weight of your car that ultimately is making you push that way. So your mass is helping to supply the push that way. But the more mass you have, the more of a push you need.
Okay. I see how that works.
Okay, so they perfectly cancel out.
That's cool.
Okay, last problem, Ferris wheel problem. A lot like the elevator problem, but this time with the Ferris wheel. And I think ultimately we're just going to calculate your velocity at or your weight at the top and bottom of the Ferris wheel. So you're going around the Ferris wheel, We want to know at the top and the bottom. At the top of the Ferris wheel you have the normal force at the top pushing you up, you have your weight pulling you down. At the bottom you have the normal force at the bottom pushing you up, and you have your weight pulling you down, right? Okay. As you're going around some Ferris wheel is going to move with some constant speed, I assume. A passenger on a carnival Ferris wheel moves in a vertical circle of radius r, so we know the radius of the sink is r, and a constant speed v. And we also know v, how fast you're moving around it. So we can get your centripetal acceleration. The seat remains upright during this. Find the expression for the force the seat exerts on the passenger at the top and at the bottom. Okay. So, I don't know. Which one should we start with? Should we start at the bottom?
Yeah.
So how hard does it push the seat push on you at the bottom of the Ferris wheel? Free body diagram for you at the bottom of the Ferris wheel, maybe. Or the total force in the y direction at the bottom. So the force at the bottom, total force at the bottom. What do you have acting on you at the bottom? You have the normal force B pushing you up minus the weight pulling you down.
Aren't they the same thing because you're not moving?
You're accelerating. You're moving in a circle.
You're accelerating or
You're moving with constant velocity around the circle, but your velocity is always changing directions. Acceleration. You have a centripetal acceleration.
Does that mean that'd be the
You have a
velocity?
centripetal acceleration of v squared over r.
And you know V.
And you know v and you know r. Yes.
Okay.
Okay. So the net forces acting on you in the y direction at the bottom is you have the normal force pushing up on you, and you have your weight pulling down on you, right?
Mm-hmm.
And you know that those net forces have to add up to your mass times your acceleration. And you are accelerating because you're traveling in circular motion.
Okay.
Good? So, we're supposed to find out, are we not giving your mass? I think we're supposed to assume that we also know mass. Anyways, so we can kind of ignore this part now. This is just the equation we were interested in, right? Let's rewrite that again. NB is equal to your weight, minus mg, your weight, is equal to m times centripetal acceleration. We'll just say v squared over r. We know what that is. Good?
Yeah.
So the normal force at the bottom is equal to, move this to the other side, factor out m times g plus v squared over r. A lot like in an elevator. This is kind of like when the elevator starts moving, your weight increases, or when the elevator stops moving, your weight increases, right? It's like you're coming down and stopping and then going back up.
Yeah.
Kind of. So your weight is increased depending on how fast you're moving around.
Okay.
Or how hard the force pushes on you is increased. Similarly, at the top, your normal force at the top is going to be, if we still want to call this direction up, should we still call that way up or should we call that way up?
We should call that way up.
Call this way up, keep it that way? So, sorry, not your normal force at the top. The total forces acting on you at the top is going to be the normal force at the top minus your weight, right?
Yeah.
And in this case, it's going to equal your mass times your acceleration. Now your acceleration is going to be negative because you're accelerating that way.
Yep.
So your total acceleration is negative.
Okay.
So now we don't really care about that. We're just looking at these two equations. So when you find n of t, what's it going to be? It shows it's going to be m times g minus v squared over r.
Yeah.
Okay? That's it at the top and bottom.
Oh, that's it? That's all we wanted to know?
That's it. That's all we wanted to know. Too easy, huh?
Wait.
Okay. So now come back to the conversation I was going to skip over if we didn't have time, but really wanted to have if we did have time. And that has to do with air resistance.
Air resistance.
Air resistance. Well, not just air resistance, but resistance for traveling through a fluid in general. Because so far, one of the things we'll talk about is air resistance, but we'll also talk about just resistance, like if I drop you and I drop you in water, what happens?
You go slower.
You go slower, but you start out, when I first drop you, you start speeding up, speeding up, speeding up, and then you reach some speed that you just stay that speed the whole time as you fall. We call that your terminal velocity. You don't keep getting faster and faster and faster and faster and faster. Right?
Yeah.
You reach some maximum value. And why is that? It's because really, if I'm talking about throwing this through air, if we're talking about you moving through water, you keep colliding with a bunch of particles. And those keep smashing into you, slowing you down, slowing you down, slowing you down. And you hit them. They provide force on you, you provide force on them. Right? Mm-hmm. Same thing as this falls through the atmosphere. So there's things constantly applying a force to you, trying to get you to slow down, trying to get you to stop. Those are resistive forces, like air resistance or drag. You with me?
Okay.
Okay. So, let's see, which one are we going to do first? So, turns out these forces are really, really complicated and really, really hard. And they're really complicated, and so we have to oversimplify. And our oversimplification is, for slow speeds, the force of that resistance, if you're moving at slow speeds, is proportional to velocity. Some constant times velocity. What do I mean by that? I mean, the faster this marker moves, this should make intuitive sense, the faster this marker moves, the more air it's going to hit.
Okay.
And so the more there's going to be a resistive force pushing back on it. There's more air resistance the faster it moves. So the resistive force is equal to how fast it's moving times some constant. Constant's going to be smaller if we're talking about moving through air. It's going to be bigger if we're talking about moving through water.
What about big object is like
Yeah, we're going to assume right now that we're talking about perfectly spherical objects. We're not even going to bring the object shape into the question, because that adds a lot of complication as well. So we're going to assume for a perfectly spherical, I think that they said assume that we're talking about a 1 centimeter. The shape and all that just affects the constant now. It doesn't affect the fact that it's proportional to velocity. So this still holds. We don't need to have this shape conversation. So the force, the resistive force, is for slow speed is going to be some constant times the velocity. Proportional to the velocity is another way to say that. The faster you go, the more resistive force you feel.
What do you mean slow speeds?
At not too high of speeds. It's not precise. This is a slow speed.
What point does it turn to fast speed?
I don't know. But a bolt's a fast speed, and my walking is a slow speed.
I'll just go from there.
Okay. Now, for high speeds, then the resistive force is d times v squared. And what constitutes a high speed or a low speed depends on the medium that we're talking about. So we're going to do a lot of oversimplifying. Turns out when you're falling through the atmosphere, so like if you go skydiving, that's now a fast speed for the atmosphere, and you use this equation. If you take a little metal ball and you drop it in syrup and watch it fall through the syrup, you'd be using this equation.
Gotcha.
What if you just run?
I don't know.
So what is D again? Is that just a constant?
Just constant, just a different letter than what we had before. The D has to do with the fact that we call it, in that case, drag. And I think in the first case we just call it resistive force. Anyways, so we're going to focus on just slow speeds for now, and then high speeds are kind of, would have a similar discussion, but we won't do as much with that one. So for low speeds, think about I'm dropping a ball now, a little metal ball in syrup. So it's going to fall through the syrup pretty slowly. So the metal ball is going to be pulled down by its weight. But then there's going to be some resistive force, F, pushing up on it, slowing it down. Right?
Yeah.
So the forces, the net forces in the y direction, are going to equal its weight minus the resistive force,
Yeah.
which is going to be mg minus k times v.
Okay.
Good so far?
Yeah.
Okay. And this is going to give you your total mass times your total acceleration.
Yep.
Because we're assuming you're just moving in the y direction. Okay, As the speed increases, the resisting force also increases until finally they are equal to each other. Okay, so notice that as time goes on, as the ball falls through the material, initially it's going to start speeding up, right?
Yeah.
And its velocity gets higher and higher and higher and higher and higher. And that's going to keep happening until the resistive force is exactly as big as its weight.
Yeah. For
So-
V equals 0.
Notice that the resistive, look at it here. As velocity gets bigger, this quantity gets bigger. And eventually it's going to get so big that it's equal to this quantity.
Yeah.
So there comes a point where mg minus k at velocity, we'll say velocity sub t for a second, there comes some velocity, v sub t, where that's equal to 0. And so your net force is now 0, you're not speeding up anymore. So you've reached your max velocity. And we call it your terminal velocity.
Terminal velocity.
Yes.
Okay.
So your terminal velocity then, v sub t, is equal to mg over k. Notice that the more mass you have, the more terminal velocity you're going to have. The harder gravity pulls you, the more terminal velocity you're going to have. And then the constant A big K means the material is more solid. A small k means it's more liquid. So a small k is like air, a big K is like water. So if you divide by a really small number, that makes your whole number much bigger. If you divide by a big number, that makes your whole number much smaller.
Yeah.
Make sense there?
Yeah.
Okay. So terminal velocity, in this case, is right here. That's the max speed that you're able to reach when the forces add up to 0. So now I think we're going to try and find an equation for your velocity. So now we know your velocity, your terminal velocity, but now let's find the equation for your velocity at any given time. Because now notice that your velocity is much more complicated. This is no longer a constant acceleration picture. Your acceleration is changing all the time.
Gotcha.
Make sense?
Yeah.
Okay. So in general, here's what we know. This is true at any given point in time. That your weight minus your resistive force is equal to your mass times your acceleration. You with me?
Yeah.
Yeah.
So I'm going to rewrite this equation. I'm going to write this side first. Hopefully we have enough space here. Your mass times your acceleration is equal to mg minus kVt, or kV, sorry. We're looking at this one, so let me look at the wrong equation. Good so far?
Yeah.
Okay, now I've got to get all my velocities over here and everything else on the other side.
Okay.
Actually, let's make a substitution that he makes, which might be nice. First thing I'm going to do is divide everything through by k. So divide everything by k, we get m over k times dv dt is equal to mg over k minus v. With me? Now, mg over k is our terminal velocity. Same thing. Your terminal velocity is a constant.
Okay.
It's the max speed you can reach. That's just some constant. So this is also equal to your terminal velocity minus your actual velocity. Good? So now I'm going to put these on this side. Ignore the middle. I'm going to put the v's over here and the mk over here.
Okay.
So we got dv divided by vt, not for all, divided by vt minus v is equal to, when we move this over here, it's going to be k over m. Right?
What about your dt?
And then we put the dt here instead of on this side. Good?
Yeah.
Now, because I don't want my variable, notice that v is my only variable here. Everything else is constant.
Okay.
And because I don't want my variable negative, I want positive, just because. I'm going to multiply both sides by -1. So I'm going to rewrite this as dv over v minus vt is equal to negative km dt.
Okay.
Good? All right, now integrate both sides. When we integrate this, what do we get? Natural log of v minus vt. Remember that? What's the integral of 1 over x? It's equal to natural log of x.
Yeah.
Oh, okay.
And then adding a constant or subtracting a constant doesn't change anything.
Okay.
Okay, so natural log of v minus vt is equal to the integral over here, negative k over m, that's all just constant, so what's the integral of dt?
Just t.
Just t. So this is negative k over m times t. And then we have plus some constant. Call it c1 for now.
Okay.
Okay, so now I'm going to do e raised to e to the power of that is equal to e to the power of that, right?
Yeah.
Now, e to the log, those cancel out each other, right?
Natural log.
To the natural log. Yeah, LM's natural log. So we get v minus vt is equal to e to the negative km, k over m times t, plus c. You with me?
Yeah.
Now, if I have x to the 2 plus 2, that's the same thing as x squared times x squared, right?
Yeah.
So this plus c, rather than plus c, I'm going to write this as times e to the c.
Isn't e to the c like 1 or something?
C is a constant, e is a constant. We have no clue what those are.
No.
C could be 57. So now it's e to the 57.
Okay.
But the point is, e is a constant and c is a constant. That was c1. E is a constant and c is a constant. And the constant to the power of a constant is a constant. So we'll just call that whole thing c. Whatever it is, who cares? Some constant.
No. Okay.
Okay, so I'm solving for v here. So now v is equal to vt, moving vt to the other side. Vt was just constant. Plus, I'm going to write my c first. C times e to the negative k over mt. You with me?
Yeah. Sure.
Yeah.
Okay. Now I still need to figure out what that constant c is. So what is my velocity at time 0? The instant this thing starts to move.
Just your constant times your.
Don't lose track of the physical thing we're doing. We're taking a little ball bearing and we're dropping it in syrup or something like that. What's its initial velocity at time 0?
0.
0. It hasn't started moving. So I know that when I plug in 0 for t, I have to get 0 for my velocity.
Yeah.
You with me? That's how we figure out what c is. Do you remember doing these simple differential equations?
Mm-hmm.
Pretty straightforward stuff.
Somewhat.
So 0 is equal to v to the t plus c times, I'm plugging in 0 for my time.
So it's just e.
0 times a constant is still 0. E to the power of 0 is?
1.
Oh, you didn't say 0. So glad. So c then is equal to what?
Vt.
Negative vt. Vt plus what gives me 0?
Negative.
Negative vt. Okay, so we figured out what the c is. So our velocity now, our velocity is equal to vt minus vt times e to the negative k over mt.
Okay.
Or v is equal to, factor out the vt, and we have 1 minus e to the negative k over mt. Now let's see if we did that whole thing right. Vt times 1 minus e to the negative k over mt. So there is our velocity function.
That's our velocity function
Yeah.
for air resistance.
All we did is, all we said, notice how stupid simple of a model we are still using. We're saying, let's just assume air resistance is proportional to velocity.
Okay.
You double your speed, it doubles your air resistance. That's all we assumed. And now that took us to this for our velocity equation, instead of v equals v naught plus at.
Oh, plus 18. Oh, okay, I see it. Yeah.
The point is, it got, our velocity equation without this, without air resistance, was v is equal to v naught plus at. We assumed v naught equal to 0 on this equation actually. So, it's the same as v is equal to acceleration times time. This is what it was when acceleration was a constant. Now all we did is said, now let's just assume that there's just a little bit of air resistance. Keep it simple, it's directly proportional to your velocity, and look at how much more complicated our math got. And we're still using a stupid simple model.
Yeah.
That's one of the points I want to stress for you a little bit here. And one of the reasons I wanted to go into this. It's not so that we can do the physics of this necessarily. It's, I want you to understand, talking about things that even seem simple isn't nearly as straightforward as it seems. So this is going beyond physics a little bit. To be skeptical of people pretending that they know how systems are going to evolve with time. Could they handle something like this?
What do you
Maybe.
mean systems?
Any systems. let's put some policy in place. What are the effects going to be? Can you predict the effects of putting some policy in place?
Not really.
How hard is it for you to talk about this thing falling through the air with a little bit of air resistance?
Yeah.
It gets a lot harder, a lot quicker. That's the point. Point is, systems, making predictions is a very difficult thing to do as a general rule. It's very hard for people to do it accurately. And there's a whole field of math dedicated to making accurate predictions based off of probabilities, actuarial math, and they are not simple, and they are not easy to do. So don't be taken in by people pretending that they know how to make these great grand predictions about how systems will progress into the future. Right?
Yeah.
Like when COVID first hit, and the initial models were like 2 million people in America were going to die. What a bunch of nonsense. And if you have some basic understanding, if you knew a little bit of computer science, a little bit of actuarial math, a little bit about systems like this, you can instantly detect all the nonsense coming through. And yeah, there's no way that that person knows what they're talking about. Stuff like that. Little sanity checks. If people can't talk about objects falling, how on earth are they going to predict how viruses are spreading through mass populations? Which one of those is easier to talk about? They're not even comparable. This is stupid simple compared to talking about spreading viruses. So don't be taken in. That's the point. Adding even a little bit of complication suddenly blows things up. And now you know why you need to know calculus to start talking about physics. Because unless you use just the stupidest, straightforward, simple models in the universe, you can't ever add even just a little bit of complexity. But that was just our velocity function. Now we know how to get our position function and our acceleration function.
Yes. Derivative and integral.
Derivative and integral. That's exactly right. So that's the next thing we're going to do. Hopefully none of these constants are important. There's our velocity. Give me some space. I'll just take the space over here. So now let's calculate our acceleration function. What's our acceleration function? Acceleration, by definition, is the derivative of velocity. So we just need to differentiate this thing to figure out our acceleration. It's that simple. Okay. So the acceleration then is equal to, break this up into two things, maybe that will help you differentiate it. Vt, put it back like this, minus Vt e to the negative k over mt, right?
Yeah.
Okay, so now we're taking the derivative. What's the derivative of a constant?
Just the constant.
0.
Are we taking the derivative or the integral?
Derivative. We're going to do acceleration first, and then we'll go back and do position.
Okay.
Just doing the easy one first. So the derivative of that is just 0, right? Because that's a constant. Remember, our only variable now is t. Everything else is a constant.
Okay.
Now over here, what's the derivative of e to the x?
X.
E to the x.
That's right.
Okay.
The derivative of an exponential is just that function. So we take the derivative of this, it's still just negative bt e to the negative k over mt. Then you just apply the chain rule times the derivative of what's inside there. And what's the derivative of that? Just negative km, right? Because that's negative km times, this is a t. So t's are only variable.
Okay.
Good? So that is equal to k times vt over m e to the negative kmt. There's our acceleration function now.
Dang, that is complicated.
Really quick, let me rewrite the acceleration function with the vt rewritten back in terms of how we had it initially. Did we erase that?
Yeah, we did.
So vt is just a constant. Vt is just a constant, and Vt is going to be equal to, we can refigure it out, mg over k.
That's right.
That's what Vt was. So if we rewrite that in here, just to make a connection, notice if I substitute that Vt in as that, the k in the numerator and this k are going to cancel out. M and that m are going to cancel out, and we're just going to be left with g times e to the negative k over mt. Can you see that?
Yes.
Okay, so notice what happens now. Plug in 0 for t. When you plug in 0 for t, what do you get?
Just G.
Okay, just g. Yeah, you jumped and did the whole thing. And then since that is a negative exponent, as times get bigger and bigger, e becomes a smaller and smaller number. It starts out at 1 and gets smaller.
Oh, that makes sense.
So your acceleration starts out g and then gets smaller and smaller with time. And it gets closer and closer to 0. Because your acceleration goes to 0 as you approach your terminal velocity. Okay, and then, I don't know if we really need the position one. There's not as much to be gained from that. You just integrate this with respect to time now to find the position function. And I don't have any good insight like I did with the acceleration. But you know how to do it. You just integrate it. The integral of e to the x is e to the x. So you just divide by the derivative when you do the chain rule, the derivative of what's upstairs. Make sense?
Yep.
And it's in your book. Okay. Last thing we're going to do, we're just going to calculate your terminal velocity. In this case, we're not going to do any calculus. We're just going to come up with the terminal velocity equation.
Because that was just slow speeds.
Yeah, so this was the case where our resistance was this equation, right? Mm-hmm. What about if your resistance was this equation? So we still have your total force in the y direction is equal to your weight minus the resistive force. But in this case, it's going to be mg minus d times v squared. This is the one that applies when you go skydiving. You with me?
Yeah.
Okay.
Okay, so we want to know when this is equal to 0. Then you've reached your max velocity. Right?
Yeah.
So what is that velocity going to be?
Velocity when you reach the max.
Well, keep this equal to Fy. So when this is equal to 0 is when we've reached our max velocity. So minus d times v sub t squared. And we'll call that your terminal velocity.
Okay.
The time where it reaches its max. So how do we find that? You just move this to the other side, divide by d, take the square root. So vt is equal to the square root of mg divided by d. And so you might be told to calculate the terminal velocity for some medium. The book will have to give you the d. That will depend on if we're talking about an air or some other substance.
Yeah.
And then you can calculate the terminal velocity based off of that.
Okay.
Good?
Yeah, that makes sense.
Okay, we got through it all. There it is. And now we can use the rest of class for any questions, homework.
Okay. Can we take a break real fast?
Sure.